I will talk about causal inference and applications to gene regulation. And I'm particularly excited right now to be working on causal inference because for the first time ever, we actually have access to very large-scale interventional data sets. So, until now, it has basically been impossible or unethical or just too expensive to perform very large-scale randomized experiments, right? But now, because of the introduction of the CRISPR-Cas system in genomics, it's suddenly possible that any undergrad can perform a really large-scale interventional study. And so these data sets are becoming more and more available. And so we have completely new questions now to ask, namely, how can we use interventional data together with observational data in order to say something about, for example, in this case, the underlying gene regulatory network, or anything, the mechanisms that actually led to this data. And so I want to just introduce a framework, a mathematical framework that has been developed for thinking about causality, so not just correlation, but actually causality, and the kinds of algorithms that we're using or that we have developed to actually learn the underlying causal system, and what kind of math goes into this as well. So let me just start off. Oops, so this doesn't work. Oh, now it works. Okay, so I take a graphical models approach. So since I want to study these very large gene regulatory networks, so in humans we have 20,000 nodes, so we would like to ultimately learn a network on 20,000 nodes. So we would like to represent these kinds of relationships in some way, and so that's why we take a graphical models approach so that we can represent it as a network. And so what are graphical models? So graphical models are used everywhere in the sciences, and they come up in, there are different kinds of graphical models that people use depending on the application that you're working on. For example, for accurate weather forecasting, which we have over here, you want to, or you need to know the correlations or the dependencies on the weather in different locations. And so there, often we use a undirected graphical model. So here the edges just tell you that there are dependencies between these places, whereas missing edges, for example, across a mountain, right? You have a missing edge because the weather will be quite independent on one side of the mountain or on the other side of the mountain. And here we usually use undirected graphical models because, the direction doesn't really matter because you can anyways not intervene on the weather in one place. But on the other hand, if you have like medical applications or biological applications, there the directions matter a lot, right? Because I want to know, for example, if you have genes, right? I want to know if I knock out a particular gene or perturb a particular gene, well, what happens to all the others, right? So, or if you have like some medicine, right? You're perturbing the system, well, what happens or what doesn't happen to some of the variables inside? And so here correlations are really not enough. So we really need to know something about the causal relationships, so the directional relationships. And so a lot of what we do is somehow, how do we go from, this is known as predictive modeling over here, all the way to causal modeling over here. And so, what is the bread and butter of, or who does a lot of predictive modeling? Well, machine learning, that's what it's all about, right? So in machine learning, and we know like all these like really amazing successes that have been come out of machine learning, and there what one tries to do is directly try to optimize prediction performance, right? Without making without having to or wanting to make any modeling assumptions about the underlying system. You just directly try to optimize prediction performance. And this has worked and works in many domain applications, but in particular in medical applications, right? This is not enough. I mean, just prediction is not enough. You really need to understand the underlying mechanisms. And so this is where we need to take a causal approach. So we need to somehow open up this black box and really get to these causal relationships. And and in traditional machine learning, so because you care about prediction, well, so then all of the methods are really made to leverage observational data. But if you want to get to the causal mechanisms, you need to be able to make use of interventional data as well. And so one of the goals of our research is really to develop a theoretical and algorithmic framework for being able to make use of observational and interventional data for learning the causal mechanisms or causal networks. So that's a bit of an introduction of, the different fields that come together and what we want to build up on, and what we ultimately want to get to, and what the motivation is for looking at these kinds of problems. And let me also set up a bit of history in terms of causal inference. Obviously, this is not new, because causal inference is, at the center of scientific discovery. So obviously, it has a very long history. So the framework was already developed in the 1920s by Jerzy Neiman and Sewell Wright. And the framework is known as structural equation models, which I'm going to set up on the next slide. What is kind of interesting is what happened then among statisticians is kind of what is happening now a bit in science, that there was a lot of skepticism that, and this was all from observational data because they didn't really have a lot of interventional data then, that you cannot really tell anything causal just from observational data. And that's a lot also of what is happening now in science, that it's that there is a lot of skepticism about causal inference. But there is the whole theory, and this also actually re-emerged in the 1970s through major contributions, mainly by 4 people: Julia Pearl, Jamie Robbins, Don Rubin, and Peter Spertus. And I put the areas where these people are working on because it just shows you how interdisciplinary this field is, right? You do have statistics, you do have epidemiology, like more applications, but also philosophy, right? Because you need to define what is actually a causal relationship. And then obviously you also have computer science. So that's where causal inference is located. And nowadays, of course, there are many, many other areas which are also coming in more and more. And here, of course, the question is also, where is pure math, and what can pure math maybe do to help the development of causal inference, which I'll talk a little bit about today as well. Okay, so why do I think now it's exciting to be working on this? As I said, so for the first time, there is like large-scale interventional data that is becoming available, and this comes out of genetics. So how does this data look like? So humans have 20,000 genes. So we nowadays, whereas maybe 10 years ago, the data sets that came out of genomics had maybe 100 cells or 100 samples. Nowadays, every one of the data sets has like measurements of 100,000 to 1 million single cells. Okay, so that's a matrix of size 20,000. Those are the number of variables times 100,000 to 1 million samples. So these are single cell measurements of all 20,000 genes. And not only can you get these measurements, but you can also get measurements when I'm perturbing any one of my genes. So for example, when I'm deleting one of these genes, and I get to see how does the expression of the other genes change. Okay, so now of course this is a huge search space. We have 20,000 genes. You can knock out any one of your genes, so set the value to 0, or even combinations of genes. So this leads also to a lot of experimental design questions. Okay, so this not only allows you to test, previous algorithms that have been developed, but also, of course, leads to completely new questions of how can we use this kind of data to actually learn more about the underlying system. So setting up the mathematical framework. So this is, in fact, exactly the framework that was developed in the 1920s that I'm going to use. It's a very general framework for thinking about causality. It's known as structural equation models. So since I'm talking about causal relationships, and you can never cause anything in the past, right? So then that means that I can represent the causal relationships by a directed acyclic graph. Right? I cannot have any direct cycles because I cannot cause anything that was in the past. So that's how I'm representing my causal relationships, by directed edges. And on the nodes, I have random variables. So these are, the nodes is what I'm going to observe, and what I want to learn is the graph. Okay, so I have observations. So think of, for example, here I have gene 1, gene 2, gene 3, gene 4. I get to observe its expression, and I would really like to learn this graph here. And so the model is this model where each one of my nodes is a random variable, and the structure, the causal structure, tells you here, for example, that this random variable x4 is a function of all of my direct causes, so x2 and x3, and some kind of noise. Okay, and these functions can obviously be nonlinear, they can be anything, they're just a deterministic function. And then we have the noise variables. They just have to be independent noise. Again, you know, some people like to assume Gaussianity, but I prefer to, for gene expression data, I definitely don't want to make any parametric assumptions. So I really want to kind of try to get to this very general model, so no assumptions on my functions here that link the different random variables, and also no assumptions on the noise, on the distribution of the noise. So now I get observations here from the nodes, and I would really like to know something, like to learn the underlying network. So that's the problem. And now also I have to think about, so what is, I want to mathematically define what is an intervention, okay? So this here is what we had until now is no node interventions at all, just observations on the nodes. Now I can intervene on the system. So the question is, what does that mean? So I'll distinguish two different interventions. One is a very invasive intervention. This is a perfect intervention. So what are we going to do? Well, you're taking some node and you're just setting it to a particular value, whatever you like. Okay, so in this case, I'm setting it to some constant. So if I'm thinking about genomics, I'm just, for example, just deleting that gene. So I'm setting that expression value to 0. Okay, so this is a very invasive kind of intervention, right? Where I'm really just setting this value here to 0. And what that means is that, well, all of my direct causes don't have an effect on me anymore, right? Because I was just set to some value, so definitely it doesn't matter anymore who my direct causes are. So I'm actually in this very invasive intervention, I'm really changing the network structure because I'm removing all incoming nodes into me, incoming edges into me. And then a general kind of intervention encompasses all other interventions, meaning where I'm not necessarily setting the value of a variable to some constant, but I can just, for example, change this edge, the function, right? So change how my causes act on me, or I can just add, for example, some noise into the system at a particular node. So these are, these are all of the interventions that are not as invasive, right? I'm not changing the graph structure. I am just changing, for example, these edges, so the functions on the edges, the causal effects, or I'm changing the noise at each one of the variables where I'm intervening on. So that's a mathematical framework for thinking about interventions. So the hard interventions in a biological setting would be these gene deletions or gene knockouts. And for example, a soft intervention in a biological context would be something like a gene knockdown, where I'm not, completely removing a gene, but I'm just knocking it down. So the expression, taking the expression down. And so this is a nice framework to start thinking about. So, the general question is, okay, so now I have some interventional data like this, some observational data. So what can we say about the underlying network? Can we develop algorithms for determining this underlying network? And also like more basic questions, maybe. I mean, something that from a biological perspective seems natural is to think that the more invasive interventions, right, where I'm actually changing the graph structure, well, they should, and that's why biologists are doing these experiments, because they think that these should provide me more information about the underlying structure, about the underlying network. So the question is that even true, right? So if I have these perfect interventions, does that really provide me more information about the underlying causal network than these less invasive interventions, for example? So those are the kinds of questions we've been asking ourselves. And then also, of course, the development of algorithms for really learning these causal networks. So I don't know if someone wants to ask questions, but please just interrupt me if there are any questions. Okay, so let's see. So let me first talk about standard methods for going about this. Okay, so I get such a data matrix, as I talked about. So these are the number of variables. So these are the number of nodes in my graph. And these are my samples. So how many observations I get. In this case now I said 100,000 samples. And so from this data, what I would like to do is I would like to learn this network over here. Okay. And now what are standard approaches for doing this? So the standard approach for doing is the following. So if I have a network, such a structural equation model as we had over here, this implies certain constraints on my distribution. Okay, so for example, it implies that, here, for example, any two nodes that don't have an edge, well, they will be independent if I condition on the right kinds of variables. Okay, in particular, if you take any node and any non-descendant of this node, okay, and I just condition on the parents of my node, then it becomes independent. These two nodes become independent because, you know, any information that a node has on its non-descendants is already contained in the parents. Okay, so somehow this graph structure or this causal relationships actually imply certain constraints on the distributions. Right? They imply all of these different kinds of conditional independence relations because, you know, a node cannot contain any information about its non-descendants once I already condition on the parents. And so a standard way of going about doing causal inference is taking this data, right, and then learning all of the different conditional independence relations that hold in the data. Okay, so this is like from the sample distribution, you can learn all of these conditional independence relations and then try to go back to the graph and say like, okay, so if I have these conditional independence relations, well, that tells me something about the graph. So it's like this two-stage procedure, go from data to conditional independence relations and then to the network itself. But now there is a problem with this approach, namely that different networks can actually encode the same set of conditional independence relations. Okay, and this is very well known, and this is known as Markov equivalence. And let me just show you on the next slide. So these are all of the graphs that actually encode the same conditional independence relations. So for example, I mean, this is very nice to see here is like, so if X causes Y or Y causes X, well, we cannot tell it apart just from observational data because the independence or the dependence relations are just X is dependent of Y, right? And it's independent of everything else because there are no other edges. But I cannot tell just from observational data if the edge goes in this direction or the edge goes in this direction. So just from observational data alone, all I can hope to learn are these Markov equivalence classes. Okay, so from observations, but at least this is already something, right? So I can just not tell if it's this graph or this graph or this graph. But that's all you can hope to do if you just have observational data. And now what interventional data buys you, and this is of course a question, is, well, if I have a certain intervention on some node, well, then obviously I should get more identifiability, right? For example, in particular, if I intervene on node X, for example, here, well, I can tell in which direction the arrow goes, because if I intervene on X, then Y changes, but here, if I intervene on X, then Y doesn't change. So, but the question is, well, what are these interventional Markov equivalence classes, right? What is the identifiability that I get when I also have interventions? And in particular, and this was now turned into a mathematical question, a question about if you have perfect interventions, right, these very invasive interventions, or if I have imperfect interventions, these much less invasive interventions, do they provide me the same amount of causal information? So mathematically, that means, do they give rise to the same equivalence classes? So is the identifiability of the graph, is that the same under perfect interventions or under imperfect interventions? So now we can start thinking about these questions really from a mathematical perspective, instead of, you know, just asking these questions maybe more colloquial. So let me talk a little bit about, you know, since causal inference has such a long history, I'll talk a little bit about the algorithms that have been developed, and this is all purely in the observational setting, okay? To the interventional setting, because there has not been such data around, there have also not been basically no algorithms developed in that setting, so I'll get to that afterwards. But I first just want to talk about this problem where, you know, just in the observational setting, how do we from data actually now learn these different equivalence classes? Right, this is all we can identify. So how do we actually learn these? And then I'll get to these questions about working with interventions as well. And so here, so this is kind of neat because it's all nice and clean because there are basically only two different approaches for doing this. And so the first approach, these are known as constraint-based approaches. So how does it work? Well, you're learning some constraints, so exactly these conditional independence relations that we saw, and now you try to find a graph that satisfies as many of the constraints as possible. Okay, so that's why it's a constraint-based approach. So I try to find the graph, so I have all of my list of constraints, the conditional independence relations. Now you try to find the network that satisfies as many as possible of all of these. And here a very prominent example is this PC algorithm that was developed by Spertus, Clymer, and Shines. And on the other hand, we have score-based approaches. So what do? So they search over the space of these equivalence classes. And since the space is very large, they do a greedy search over the space of equivalence classes. And now I have to give you a score function. And usually the score function they use is some penalized likelihood score. Okay, so you start in the empty graph and you add the edge that maximizes the score function, and you continue adding edges. And in this particular greedy equivalence search algorithm, then you start removing one edge at a time until you cannot improve the score. And this algorithm is in fact consistent, so it actually will end up in the correct graph or in the correct equivalence class, which is very interesting. That doesn't usually happen with these greedy algorithms, right? That you just have to go all the way up, so always add edges and then remove edges, and you actually get to the correct equivalence class. And so now we can use some kind of nice math, I think, some nice actually methods from algebraic geometry and combinatorics to understand when do these algorithms work and what are the advantages of one algorithm versus the other algorithm. So, and let me just give a bit of intuition. So it turns out that score-based approaches, they're usually much slower, okay? And we'll see afterwards, this leads to a lot of combinatorics questions, but this is the case because it's doing a greedy search over a huge space. And we'll talk a bit about how big is the space of Markov equivalence classes on the next slide. But that's the intuition for why these approaches are usually slower. However, score-based approaches usually have higher accuracy when I give you a fixed sample size, like n observations, then usually you actually perform better with score-based approaches instead of constraint-based approaches. And there again, so the intuition is that constraint-based approaches, well, if you get the constraints wrong, the algorithm is actually going to do very badly, right? But the constraints are estimated from data because these are the conditional independence relations that you're using as constraints. So you need to have a lot of samples in order to be able to get the constraints right, and then your algorithm is going to do well. Whereas in the score-based approaches, because you're doing a greedy search, even if you're not getting the constraints, or in this case the score, exactly right, you're still often going to end up in the correct equivalence class. So that's kind of the intuition. But to really get this straight, we need to analyze it a bit more mathematically. And so here I think it leads to a lot of very interesting combinatorics and algebraic geometry questions. But maybe before I get there, already something to see, and this is a big open problem, so that I also point out some open problems here, is so you saw here something that happens a lot in statistics is you have certain algorithms, or you have algorithms like score-based approaches that are slower, but perform better with a fixed sample size. And then you have other algorithms that are maybe faster, but they perform worse with a fixed sample size. And so this is known in statistics that there is always this trade-off between statistical properties and computational properties. And now this has been studied for various problems, but for causal inference, it's completely open. Okay, so we don't know this optimal trade-off between statistical properties and computational properties. We don't know if these two algorithm classes actually lie on this optimal curve. And we basically don't have any points where we know that they definitely lie on this optimal curve. So this is a completely open, but you see an instance here that you see this trade-off actually happening for both of these classes. Okay, so let's analyze the advantages and disadvantages a bit more. And here you see like a lot of nice mathematics entering into the game. Let me start with score-based approaches, where I said probably the reason why they're actually usually slower is because the space of equivalence classes is so large. And let's look at that. So here, okay, so first another open question. So we actually don't have a formula for the number of equivalence classes on P nodes. Okay, so this is completely open. However, Gillespie and Perlman, so they wrote a very nice paper, which is completely computational, where they were able to enumerate all equivalence classes up to 10 nodes. And so here you see how it explodes. Okay, so the space is really pretty large. So you already have, I think, 10 to the 19 many equivalence classes on 10 nodes. So this is one open problem. They also reported some other very interesting facts here. which are interesting from an interventional perspective. So what are these things? So here you see some numbers which seem to converge to something like a quarter. And what is this? So this is the total number of equivalence classes divided by the total number of DAGs. So they call them acyclic directed graphs. So this tells you that an average, an equivalence class is, it seems like it converges to about a quarter. So an average, an equivalence class has about 4 graphs in it. And so that's interesting because it kind of says that the picture, even if you have very large graphs, kind of looks like this, that every equivalence class is pretty small. Okay, so that even from observational data, you're actually pretty well able to identify the graph, meaning that you need very few interventions in order to really identify the underlying causal structure. Now, again, this is a conjecture, but a very important conjecture in terms of thinking about, you know, how many interventions am I expected to need in order to be able to identify the underlying causal structure? And the last column, again, a conjecture, so it seems to converge to something like a quarter or something higher than a quarter. So what is this? So these are the number of equivalence classes of size 1 divided by all equivalence classes. So this seems to suggest that about a quarter of the Markov equivalence classes actually only have one member. Okay, so again, kind of that the picture looks like this, that you have quite a few equivalence classes that just consist of one member, meaning that observational data is actually enough to already identify the underlying graph, that you really don't need any interventional data in order to figure out the underlying causal structure. So these are all important conjectures that someone in combinatorics would be very well able probably to prove. Yes, so I think it's just interesting. There should be a lot more crosstalk between all of these different areas in mathematics. So we have some papers on this, just basically stating the problem, some hardness results here and some results looking at random graph models. But I think, you know, without even looking at random graph models, I think it should be possible to at least get some formula, some recursive formula for the number of equivalence classes, similarly as there is a formula for the number of DAGs on P nodes, and also to prove something about these sequences would be very interesting. So, but this indicates that the space of equivalence classes is very large, and this might actually mean, or this might explain why these algorithms are pretty small when they perform greedy search on the space of equivalence classes. Okay, so this is where combinatorics enters in. Let's also talk a little bit about these constraint-based approaches and give a bit more background on why we think that, you know, they really need a lot of data in order to get the correct output. So, okay, so how do they work again? So constraint-based approaches, so you take the data and you estimate your conditional independence relations, and from there you estimate your graph. In particular, you just believe that, you know, you just remove edges whenever there is a conditional independence relation. Okay, if two nodes are independent from each other, well, then there is no causal link between them. So you just remove the edge. But that, and here you see the influence of philosophy. This is known as the faithfulness assumption. So the distribution has to be faithful to the graph. So this is really an assumption, right? It says that, well, this is how the algorithm works. So if I find a conditional independence relation, I can just remove the edge. But this could happen just by chance because causal effects can cancel out, right? So here is just an example of this. So say you have some strong medicine that has a positive effect on your lung functioning, so it helps the lung, but it has a negative effect on in your immune system. Well, and of course, a well-functioning immune system also helps your lung to function well. So it could be, right? I mean, there are definitely such cases where, you know, this negative effect here is as strong as the positive effect here, so that these effects actually just cancel each other out. And in this case, in the data, you would actually observe that, you know, your lung functioning and taking the medicine or not are independent from each other. Okay, just because these causal paths cancel out. But now the algorithm would make a mistake because, you know, if you have an independent statement, you're actually going to remove this edge here. And so this is known as the faithfulness assumption. And so the question is, so, I mean, it was argued when this assumption was introduced that, well, this doesn't matter that much because it anyways has measure 0, basically, right? Because it was argued that, well, you know, when does it that the causal effects exactly cancel out? Well, that's very unlikely because it has measure 0. But now the problem is when you work with data, right? So when you work with data, even if in the true model you have two variables that are independent, if you only have n samples, you're never going to be able to measure that the correlation is exactly equal to 0. You'll always get some small correlation, and then you have to introduce some kind of cutoff value, which says like, well, if I observe a correlation that is smaller than this lambda, well then, you know, then I can just assume, or I will just assume that in fact they should be independent. Okay, so I will be removing this edge. So it means that I don't need something like a faithfulness assumption. I need something much stronger when I work with data, right? I need that not only are variables dependent when there is actually an edge, but they have to be you know, bounded away from 0, right? So that I'm not just going to remove them because I'm actually working with data. So this is a strong faithfulness assumption. So we wanted to know how strong is this assumption, right? Is this really an okay assumption, or is this maybe exactly the reason why, you know, these kinds of algorithms need a huge amount of data in order to be able to work well? And so let me just show you this, and here comes a bit of math, but it will be nicer on the next slide. So let me just analyze this assumption, this faithfulness assumption, for just a very small graph so that I can actually draw out everything. So here I just have a 3-node graph, so my 3 random variables, and I'm taking the simplest model possible. So each one of my causal effects is just linear. Okay, so each one of my causal effects is linear, and all of my noise terms, they're just Gaussian. Okay, so this is a linear structural equation model with Gaussian noise. And so we don't need to go through the whole math, but then I can, you know, this implies that the distribution of all of my nodes is Gaussian, and I can figure out what the covariance matrix is. And in this case, I just wanted to have only 3 variables so that I can really draw out everything. So the covariance matrix is some function of my 3 variables. And so now what does it mean to be unfaithful? Well, here I have all causal effects. So an unfaithful distribution is any distribution that satisfies some independence relation, right? Because then if you have an independence relation, you're going to remove the edge and you're going to make a mistake. Now in the Gaussian setting, it's very nice. Namely, all of these independence statements, I can actually write them out as functions of my covariance matrix. And I don't really want to go through this, but in the Gaussian setting, it's always the case that any conditional independence relation actually corresponds to a polynomial equation in the covariance matrix itself. So in the entries of the covariance matrix, or its inverse, doesn't really matter. Okay, so I get for every conditional independence relation, I actually get a polynomial equation in my variables, which are just these causal effects. So what does it mean now? So it means that my model, the underlying true model, for me to be able to estimate it, well, it has to be bounded away from any of these bad places, right? In all of these places, I'm actually not going to get the model correctly because I'm just going to remove some edges in a wrong manner. And so this means that I have to be bounded away from these hypersurfaces, right? These are 0 sets of polynomial equations, and I can draw them because I'm in 3D. That's how I chose this example. And so here they are for this little graph. Okay, so I can learn models that are bounded away from all of these hypersurfaces. I can only learn models that are bounded away from these hypersurfaces, at least using these constraint-based approaches. And so you already see that. And you know, this is just a very small example, but you see that if you start fattening up all these hypersurfaces, then suddenly there is very little space left, okay? In particular, we analyzed, well, when does it fill up the whole space? Okay, so now you get into nice algebraic geometry questions, right? You have these hypersurfaces, you want to fatten them up, and you're asking when does it fill up the whole space? And we were able to do this for, you know, like thinking about the setting where you have the number of variables go to infinity and your number of samples go to infinity. And you can show that this is really bad. Basically, you can actually show that, you know, the networks have to be pretty small and your data size has to be very, very large for you to even have any space left after you're fattening up all these hypersurfaces. So this kind of really nicely explains why these algorithms don't work, right? Or, I mean, why they need a lot of data in order to work. Right? Because the more data you have, the smaller is your threshold that you can use in order to, you know, say that in a conditional independence test, for example, you're saying I'm fattening. So then the more data you have, the less I have to fatten up all of these hypersurfaces. So that's kind of the explanation here. So this tells you a bit about constraint-based approaches, why they need so much more data. And then we had the score-based approaches, why they usually are quite small, slow because of the large search space. So that's somehow where causal inference was. And so we were thinking a bit about how do we get around these problems. And one way of rethinking causal inference somehow is just taking a step back and thinking about, so we want to learn a DAG, right? A directed acyclic graph. And we know from, for people who study graphical models, it's actually quite easy. So the problem of learning an undirected graph is much, much easier than the problem of causal inference. Okay, so many things are known about learning undirected graphs, which are just, not known or not possible or hard for causal inference. And so we wanted to somehow break apart the two problems. Like one is an easy problem of estimating undirected graphs. And so the hard problem is really just learning the right ordering, right? Because if I give you an ordering and I give you the corresponding undirected graph, well, then you get a DAG because I can just orient all of my edges according to the ordering. Okay, so I can really see the problem of learning a DAG as the problem of just, well, because it's easy. So if I give you an ordering, it's easy to learn an undirected graph. Well, I can just see the problem of causal inference as the problem of learning the correct ordering of my variables. Okay, and now an advantage of this, and hopefully, this is how we're thinking, we can get around the computational bottleneck, is that the space of permutations, well, okay, we don't know how large the space of equivalence classes is, but it seems to be a constant times the number of DAGs. So, or at least on 10 nodes, then what we saw from the computational paper, we only have 10 factorial many permutations, whereas we have 10 to the 19 many Markov equivalence classes. Okay, so the space of permutations, and of course the proof is missing because we don't know the number of equivalence classes, seems to be much smaller than the space of Markov equivalence classes. So a much smaller search space to operate in. And so we wanted to do a greedy search in this space. In order to do a greedy search, I need to tell you a score function that we want to optimize. And I need to tell you how do I do greedy search on permutations. Okay, so I'll tell you both of these things. What I don't want to talk about is something that is well known, namely how do I associate to a permutation undirected graph. Okay, so these are just certain conditional independence relations that one does. And this is well known and has already been studied before. So I'll just take that as a black box input. I give you a permutation, we know how to get out an undirected graph. So the score function that we're going to use is very simple. We're just going to count the number of edges in the undirected graph. Okay, so that's motivated by Occam's razor. You want to have the sparsest model possible in order to represent your data. And that's exactly what we're going to use as a score function. So that's why we call it the sparsest permutation. So to every permutation, we associate an undirected graph, and the score function is just the number of edges in this undirected graph. We want to minimize that. Okay, so now I still need to tell you how to perform a greedy search in the space of permutations. So what is a neighbor in the space of permutations? So here a nice geometry comes in. So the space of permutations is actually a polytope. It's a polytope. So here I'm showing you the space of all permutations of length 4. So you see every vertex corresponds to a permutation. So it always is this is known as the permutahedron, this polytope here. And so greedy search means I'm walking along the edges of this polytope. Okay, so say I'm in, and actually it's well known, this polytope has been well studied. So say I'm in this vertex here, this ordering of the variables 3, 1, 2, 4, then who are my neighbors? So my neighbors are given by neighboring transpositions. So my neighbors are guys where I can either transpose the first two elements, so 3, 1, 2, 4 goes to 1, 3, 2, 4, or I can transpose the next two elements, so 3, 1, 2, 4 goes to 3, 2, 1, 4, or I can transpose the next two elements, so 3, 1, 2, 4 goes to 3, 1, 4, 2. Okay, so this is a general phenomenon. It's also for, when you have the permutahedron on longer permutations, your neighbors are always given by neighboring transpositions. And so my greedy search algorithm is, in terms of this polytope, you start in any permutation, you compute the corresponding undirected graph, say that has, I don't know, E edges, and I look at all of my neighbors in this polytope, and I compute the undirected graphs corresponding to these neighbors, and I see how many edges do they have. If they have less edges, I'm just going to walk there. Okay. So this is a very simple algorithm, and in fact, it is consistent, meaning you can start anywhere in this polytope, and you're actually going to end up in the correct equivalence class of graphs. Okay, so you get the same consistency guarantees as they had for greedy search in the space of Markov equivalence classes, but in a much smaller search space. And also, instead of being a parametric approach, meaning, because in the greedy search over the space of Markov equivalence classes, the score function is usually a penalized likelihood function. There you have to assume, for example, Gaussianity and linear relationships of the causal effects. Here, because the score function is just a number of edges, it's completely non-parametric. So you can just do conditional independence tests. That doesn't matter on, do you have Gaussian noise or do you have any other form of noise? So that's another advantage. Maybe and this is just for people who like geometry, this is not something that helps you very much in terms of causal inference, but I just want to point out one more thing that is kind of nice. So here's how the algorithm works. So you see that here suddenly I have a smaller polytope. And really, when we're doing our search, we're actually not doing it over the whole space of permutations, but over this slightly smaller space. And let me tell you what the intuition is for this. Let me maybe look at this kind of graph. So if I have a DAG, like for example this one here, right, where I have a missing edge between 1 and 2, well, then we already know that the permutation, when I'm switching the order between 1 and 2, since there's no edge between them, will lead to the exactly same DAG. So since my score function is the number of edges, it doesn't make sense to search over graphs that have, to search over permutations that correspond to the same graph. Right? Because we already know that the score function is not going to change. So what we did is we define, so we're taking this permutahedron and we are just gluing together, so contracting edges for different nodes that correspond to exactly the same graph. Okay. Now in general, and this is something kind of crazy, so in general, if you take a polytope and you just glue together different edges, that doesn't give a polytope. Okay, what happens here is actually it does give you a polytope. So if you just glue together these edges that correspond to the DAGs that are just the same, actually what you can prove is that a polytope comes out. And so this polytope has been studied in the undirected setting. It's known as a graph associahedron. And so here we actually define the DAG associahedron, so the same polytope in the directed setting as well. And so really when we're doing our search, our causal inference search or our greedy search over permutations, we're actually doing our search in this slightly smaller space instead of the permutahedron. So it's just kind of nice math that also is actually very useful in terms of running the algorithm itself to speed it up even a bit more. And so here is an example. So if you start on some vertex, randomly chosen vertex, you look at your neighbors, you compute the corresponding undirected graph. Obviously, the permutation, the ordering of the variables gives you also a DAG out. You just count the number of edges in each one of them, and then you walk to the sparsest one. And then you continue your search. And when there is no more sparser neighbor around you, that's what you output. And we can prove that that's actually the correct causal graph, or the correct equivalence class of graphs. Okay, so that's one approach of how we try to overcome some of these problems. And now I would like to just know, is it 45 minutes or when should I stop? 50 minutes? I don't hear anyone.
I actually,
okay.
I don't know either.
I think 50 minutes, right?
Yeah, 50 minutes.
Okay, so I'll just do 5 more minutes. Is that?
Right.
Yeah.
Okay, sounds good. So I'll try to just add in the interventions. Okay, so now that we have an algorithm which works on the observational setting and overcomes some of the problems that we have seen before, we can start to go back to these interventions that I had defined. So here, for example, if this is the graph, and now you have an intervention on node 4 or an intervention on node 3 and 5. Now we have data from all of these different graphs. We would like to be able to learn this underlying causal network here. And there has been so maybe I'll first, okay. So what has been already done is characterized this identifiability question. So how much more, so we had these Markov equivalence classes, how do they break up when you have perfect, these most invasive interventions. Okay, so this has been shown by Hauser and Bühlmann from ETH Zurich. And now kind of surprising, and this is what I alluded to, what we showed is that independent if you have perfect or imperfect, so the invasive or less invasive interventions, actually these equivalence classes are the same. So you do not gain any more information by performing these more invasive interventions as compared to these less invasive interventions. And so that's kind of a nice, at least when I talk to biologists, that's a nice kind of result, right? Because that really tells you something about the experiments you should perform, or the experiments that it's actually not even worth putting in more money to doing that, because they just don't give you more information about the underlying causal network. And in terms of algorithms, maybe just briefly, so there has been, the score-based approach has been generalized to the interventional setting. It was conjectured that that algorithm is consistent, but we proved that it's in fact not consistent. So even if you have an infinite amount of data, it's not going to, in general, output the correct graph. But the permutation algorithm is actually very easy to put into the interventional setting. And that's just kind of, it's very easy to think about in the perfect setting, when you have perfect interventions, right? So when you have perfect interventions, so if I'm intervening on a node, say variable 2, then I'm going to remove all of the edges that are pointing into me, because I'm just setting this variable to a particular value, so my causes have no more effect on me. And now if I'm doing my permutation search, well, it's actually kind of nice that you can use the interventions to reduce the search space, because I don't have to search over interventions where I'm going to make a variable point into me if I'm an intervention. Okay, so I'm using the same algorithm, but I have a reduced search directions, which are given by the interventional data, which is kind of nice. So you can use the interventions in two ways to get better identifiability, but also for actually getting better computational properties of the algorithm. And maybe I'll just go to, showing you also how this kind of stuff works. So we have simulations, obviously, where, you can run it on hundreds of variables, not thousands yet, but at least hundreds of variables. But I cannot, for large networks, we usually don't know the truth. So only in simulations we know it. So that's why I'm here showing it to you on very small networks, because there are only very small networks where biologists would agree on what the truth is. So here is a very small protein signaling network, and we show you how it works. These are ROC curves, so you really would like to be, far up and far here. GIS is the algorithm which we proved is not consistent. And then we have our two versions. So one is the one for perfect interventions, and this one here is the one for general interventions of the permutation algorithms. And this is kind of nice. What you see is that for both of our versions of the algorithms, the points lie often on top of each other. And that makes sense, because in this particular experiment, the experiments that they performed, the interventions that they performed, were actually supposed to be perfect. So it's good that they're lying on top of each other. So this is to recover directed edges. This is to recover the skeleton, just the undirected edges. So this seems to work pretty well, but I also want to just maybe leave you with how much more work is actually necessary to be done. So this is newer data where single-cell RNA-seq data. And so here again, so they have, they looked in this particular paper, I mean, the data is available for all 20,000 genes, but here in this particular paper, they just analyzed the 24 genes, so we went with that. The ground truth is not known, so we just always leave out one intervention, try to predict it based on the other interventions. So again, so this is just a proxy for, what is the ground truth. But you see, this is kind of interesting. So you have this provably not consistent algorithm, which is below the line of random guessing. But also what we're doing is not much better than random guessing, right, for this kind of data set. But the advantage of actually knowing exactly what your assumptions are, or that you know exactly what you have to work with, right? And where you have to make some more, or what are the assumptions that are actually violated here. And I think one thing we know, what is violated in this particular data set, is that there are a lot of off-target effects. So meaning you assumed, so this here, they tell me that they intervened on a particular node, but actually in these knockout experiments, you will have interventions on many other nodes as well. But we're assuming that we know exactly where the intervention took place, and probably that is one of the big reasons why we're actually not getting better performance here, or not much better performance than random guessing. So I think there is still quite a bit of work to do here for us. But that's the nice thing about having provable guarantees. You know exactly what your assumptions are, and hence something has to be worked out of these assumptions. Okay, with that, let me just go to, so here we have some other biological applications, which I will skip. So here I talk just about this edge between causal inference and gene regulation, but we take it all the way also to early disease diagnostics. And we have here some more biological review papers that we just recently wrote, if this is of interest. And so all of this work wouldn't be possible without an amazing group, and in particular, the people who really did most of the work that I talked about here were Karen and Yu Hao, two PhD students of mine, a master student of mine, Chandler, and the former postdoc, Liam. Okay, and with that, thanks.
Thank you, Carolina, for a wonderful talk. I imagine there might be some questions. So maybe we'll start with State. Are there any questions from there? Seems like there aren't. What about UW?
Yeah, we've got one question. Here, Hola.
So, if I'm understanding what the discussion is about, and I certainly hope I do, we're talking about a network of nodes which interact with each other, and influence each other's relative, which influence each other over time. And I was just kind of thinking, well, at some upper, it's probably not relevant for at this point, but on a theoretical level, there is a upper limit to the size of a network, just merely by the fact that there's only, by merely the fact that it takes time for a node to influence another node, right? We talk about the medicine we use to help somebody's lungs actually helping those lungs, but it takes time for that to happen. So likewise, that lung might influence something else and that to something else and so on, but that series takes more and more time. And so at some point, we might not even care that there's extra nodes outside of what we're talking about. And I was just wondering if the research on this actually is at that point that we can actually talk about that possibility.
Mm. Yes, okay, so this is a good question. So there are two different ways of modeling this. So here, since I didn't put in time, I mean, so you can model time and see this as additional edges, but here I'm thinking of it at stationarity. So at stationarity, you're getting to observe somehow the causal relationships that were behind it, that were behind giving rise to this distribution. Now, if you want to model it over time, you can do that as well, but still you will still have this underlying network at stationarity. But in addition, you will have, you know, all of your timestamp data that you can collect. And then you have edges going forward in time over all of your variables. But here I'm just looking at the data that is collected at stationarity, and I would like to understand what gave rise to that. So basically all of the time series gets mapped into one node. So every variable gets mapped into one node. But there are also, I mean, other people actually model it over time, and you can use exactly the same models for modeling it over time. But then we don't, I mean, since you're trying to just model the data you have, well, if you have timestamp data, you're not going to ask like what happens afterwards, because I just want to know what are the edges that is in my data. So if you're modeling it over time, again, what are the edges that are there? So we're not trying to predict something of how do these sequences behave later on.
Thank you. Got it. Thank you.
Okay, other questions?
So your original model had genes as columns and, let's say, samples as rows.
Yep.
Would it make sense to consider a dual view, as in look at samples in the gene space, and what would the whole framework that you described be able to tell about maybe the underlying structure if you apply the same kind of framework for that dual graph.
Yeah. This is very interesting. So then you have a network over cells, right?
Mm-hmm.
And so this is a lot of what people do want to know about how do different cells interact with each other. Therefore now it's, for example, in a tissue environment, you have different cell types and they have to work together, or, you know, when you have cancer development or things like that, what are the cells that help these cancer cells become metastatic, for example. And so there, until now, I mean, there's not that much yet. So people would usually do more undirected graphs, but I have not seen anything in terms of causal inference, which would be very interesting. It's a bit harder because, so usually, so because you want to look at it in terms of tissues, very often you have imaging data instead of expression data. And so in imaging, you know, expression data is kind of nice because gene 1 always corresponds to gene 1 in the other cell. So you have like a coordinate system. But with images, you don't have a coordinate system. You first have to somehow embed them into a joint coordinate system. And then you can do these kinds of graphical models approaches there. But then you don't have multiple samples of the same cell, etc. So it's a bit very other kinds of problems that appear there. But definitely something which is of great interest to actually do, to have models over cells instead of over genes. Yeah. Mm-hmm.
Further questions? Okay, if that's not the case, then let's I'll thank Carolina again for a wonderful talk.
And thanks again for UW for hosting. And I've seen a lot of our states represented there. So anyway, kudos to everyone, and thanks, Caroline, again.
Yeah, thank you very much. Bye. Thank you.
Bye.
Yeah. Goodbye.